home page right here. If you click on Files, and over here on the right side, you'll see Packet C through Test 2 Solutions. I told you I'd provide you with the answers. I believe if you click on it, it will probably try and open it, but you can download it also. I think I downloaded it already. Yeah. So the red is, I believe the red are the answers to these, okay? And it's just answers, but it's still better than nothing. And again, big asterisks on top of this. I have not checked all of these for correctness, so I think we saw in the beginning some of these things can be off. So I didn't make the keys, so don't blame me. All right. Test is on Tuesday, right? Our exam is on Tuesday. Last time I gave you like a list of problems to study. I haven't done that. I'm going to do it. I'm going to send it to you in an email. It's going to be like, here are the problems to look at. Focus on these. You'll be good. All right? Yeah, because I'm going out of town tomorrow night, and I'm going to be gone until Monday. So I'm going to try and do it tomorrow during the day. Yeah. All right, so we were graphing parabolas, quadratic functions last time, and there was a lot of homework in there. Was there anything that you wanted me to go over? Any problems that you did that may have caused any issues? I don't usually ask for questions on homework, but today I think, especially before I move on, I want to make sure everyone was comfortable. Yeah. No. So you all did perfect on them, you think? Okay. Sure. We did do a problem that I counted as credit when y'all weren't here. At the very end, remember I had you all work, and then yeah, okay, all right. So, yeah, but I gave you credit for coming up and showing it to me, and I let you leave, remember? So, yeah. We'll work something else out, okay? All right, so you just want a problem kind of to warm up here? All right, so let's sketch the function. Now, I'm going to make this one ugly, okay, because the one we did in class at the end was real nice. It factored nice. Everything was beautiful. This one, not so much, okay? This one's going to kind of suck. Negative 3x squared plus 12x plus 2, let's go, $19. So we want the seven-step process, I guess, if you want to call it, what we did for this. Anyone remember the first step? Yeah, make sure it looks like a quadratic, right? Is this quadratic? Quadratic, yes. Yes. Okay, so second thing was, which way does it open, right? This one opens down. It opens down because A is what here? Negative 3, and because it's negative, it opens down. So I know my graph is going to look like this. And that means that even though I don't know what the vertex is, I know that that vertex is going to be that point that's on top. Let me silent my phone quickly here. There we go. What was the next thing? Find the vertex. And to find the vertex, use the formula h is equal to negative b over 2a. And for us in this problem, b is 12, isn't it? So negative b would be negative 12 over 2 times a, and a for us in this problem is negative 3. So negative 3 here. It gives us negative 12 over negative 6, which is positive 2. Now please understand that in the problems that I gave you last time and today's problem, every time we found h, hasn't it turned out to be a nice number? If this were instead, let's say, 4, this would have been negative 12 over 2 times 4, or negative 4, doesn't matter. But this thing would not have reduced to be a nice integer. It would just have been a fraction, right? I'm just preparing you. I mean, like, on the test, I plan on making this a nice number. But in the reality, the big scheme of things, that's very seldom a nice number. It's usually a fraction. Okay, we found h. Now we need k, right? So to find k, we plug that answer 2 into the original function. No, that's what the y-intercept will always be. Because that's what you, to get the y-intercept, you plug 0 in for x. And that would kill off everything except the c. But that's y-intercept, not the y coordinate of the vertex. So we plug in 2 into this. So negative 3 times 2 squared plus 12 times 2 plus 19. So order of operations, square your 2, you get 4. Multiply times negative 3, you should get negative 12 plus 24 plus 19. And then collecting everything, I think it's 12 plus 19. What's that? 31? Okay. So our vertex is the point, right? This is a point on our graph, 231. Yeah, so now we just do a quick graph, right? That was the 4th step, a quick sketch of this. And really, I mean quick. It does not have to be like it's not going to be your final version. It's just to figure out what. Why are we doing quick sketch? To see if it has X-intercepts, right? That's the whole reason. So I would move to the right 2 and up 31, which is way up there. I'm just going to say it's up here. And then which way does this parabola open? Down. So if it opens down from that point, it looks like I'm guaranteed to have 2 X-intercepts. So I'm going to need to go find those 2 X-intercepts then. All right. Is that step 5, X-intercepts? 6 is Y-intercept, 7 is sketch, right? So step 5, the X-intercepts. I'm going to put a little check mark next to this. I'm going to say I should have 2 of them, right? Just kind of reaffirming what the picture just told me. I should get 2 separate answers right now. How do we find the X-intercepts? So you set the entire function, right, that you were given equal to 0. Was that the right? Was it plus? It's plus 12, right? Yeah, it's plus 12. Uh-oh. Okay, so we know that when we do this, we're supposed to get 2 answers. They're not going to be imaginary numbers. If they're imaginary, we messed up because we know from the picture we're going to have 2 nice numbers. Well, 2 real numbers on the x-axis. This does not look like it's going to factor. And if it doesn't factor, then the only other option you really have is a quadratic formula, right? So quadratic formula, QF, quadratic formula, is x equals negative b. Tell me what negative b is. Negative 12 plus or minus square root. Here we go. B squared, 12 squared, which is 144, minus 4 times negative 3, which is A, times 19, which is C, over 2 times negative 3. So I'm not writing the formula down again because I think you probably have that in your notes somewhere. And I told you that you should focus your attention on those three numbers, treating a 4 as a positive 4, break out your calculator, and do what you got to do. Yes. Yes. Treat it as a negative. Okay. This is a minus sign. So what's in yellow, you figure out what that's going to be first. So you do your 4 times -3 times 19. No, ignore the blue for now. All right, ignore the blue. What's in yellow is -228, right? What's in yellow? So I'm just going to write this down so we have it again. It's 144, then here's my minus, and then when I multiplied everything in yellow together, I got -228. That's what I got. And since I'm subtracting, right, here was that subtraction symbol. Since I'm subtracting a negative number, it's the same as adding. So 228 plus 144, 372. Understand? Now, we need to try and figure out if the square root of 372 simplifies, which can be kind of a pain in the butt. But we are trying to graph these on the x-axis, right? These are points. These are points. So because these are x-intercepts, because I have to graph them, I actually want them to be decimals, because it's easier for me to graph a decimal than it is to graph a square root of 372. I don't know where. Do you have any idea where that is? Like what number that is? And of course, if you take the square root of 372, you get 19.287 something. But it would have been a little difficult to know, oh yeah, it goes right there, right a little bit past 19 on the x-axis. It would have been hard to see that, right? So I'm going to first, just on my calculator, say this is approximately 2 decimal places, 19.29. That will replace the entire square root over here, right? Okay, so here, x equals -12 plus or minus. No more square root symbol, right? You already took the square root. All over -6. And remember that division bar. I know some of you, we talked about this last time. That division bar goes all the way across, which means you have to resolve everything up here first before you divide by -6. So we have two different scenarios here. We have when we add and when we subtract. Do you remember me doing this? I did like 2 different cases. The first one would be -12 plus the 19.29 over -6, which is, what do we have there? 7.29 on top, divided by -6, which is approximately, I'm getting about -1.22. Anyone else get something like that? Yeah. On the other one, -12, take away 19.29 divided by -6. You should have -31.29 on top. Then divide that by -6. -5.22 approximately. Oh, negative over negative. Yes, thank you. Questions? All right. Step 6. The Y-intercept. All we do there is plug 0 into the function, which kills everything off except the 19, right? So here we go on my last step. I'm going to draw my graph. So I'm going to start on a fresh sheet here. I'm going to cheat a little bit. You don't like that? What that? You don't like that? Now I'm really cheating. No, I don't need that. All right, so when you do this, think through things first. Where is your vertex? It was what? 2 and way up at 31, right? And then your Y-intercept was 19, and your X-intercepts were like negative 1.22 and 5.22, right? So that gives you some idea of the scale that you need to draw this with. On my x-axis, I only really need 5 or 6 units each way, right? Would be the most I would need. But in the y direction, I need to go all the way up to 30-something. So when you draw this, it's perfectly fine to do this. 1, 2, 3, 4, 5. Let's say that's 6. And make sure you put at least 1 unit marked so that I know, or whoever's reading this knows, that each of these ticks represents 1, right? If I put a 6 out here, that means each of these had to be a 1. But when I go up, I'm actually going to count a little different. I'm going to count by 5s. So I'm going to say that that's 5, 10, 15, 20, 25, 30, 35. And I can mark it up here 35. This is totally allowed when you're graphing something to change the scales. That's legitimate. What you can't do is this. You cannot come in here and say, oh, and I'm going to make that negative 5, negative 10. You can't change what one of these little spaces means on the x-axis on either side. The x-axis always has to be consistent. 1 unit is 1 unit. The y-axis has to be consistent, but they don't have to be consistent with each other. Understand the difference, or what I'm getting at here? Okay. All right. I should probably put a negative 1 and a negative 2 here because one of my x-intercepts is negative, right? All right. Start with the vertex. I go to the right 2. I go up 31. 31 is somewhere up there, right 2. We just try and get ballpark idea of where it is. And just to be clear so that my instructor knows, was it 31 or 32? It's 31. I'm going to label the point so everyone knows what it is. And then I have my x-intercepts were next. They were at negative 1.22. So negative 1 is right here, a little bit to the left of it. And see, we don't have to be perfect, all right? It's good enough. 5.22, somewhere around there. We agree? Y-intercept is 19. 5, 10, 15, 20, so right below 20, like that. My axis of symmetry is this imaginary line that goes through here. I'm just putting that there to help me graph it, to kind of keep it looking like a mirror image of itself. And also make sure that it looks like a U and not a V. Remember I said you could add more detail if you want. If you want to tell me what the axis of symmetry is, x equals 2, right? That's the x coordinate. You could label these points if you want. You could say that's the point 5.220. This point over here is negative 1.220. Right, I'm referring to those. I could label this point to be the point 0, 19. I could even really try and get a lot of, credit here. I could label the function negative 3x squared plus 12x plus 19, right? This is the graph of that function. Here are all the points. Well, when you came up, I saw different work, and I know some of you did really, really good graphs, and some of you did kind of the minimum, but good enough, What I did see a lot of disparity in when you came up and I checked you off was who's showing steps, like the process. Some of you are not actually saying, okay, 1, do this, 2, do this, 3, do this, just kind of doing it all together at one time, which I would just caution you, because if you can do it without having to work it out in steps, that's fine, but if you get hung up, I'm not going to have much sympathy for you. There's a kind of a bigger underlying thing to that. I think we established in the very beginning, like, the reason why you're here, and like this is your last math class and all that, right? We talk about the difference between having a degree and not having a degree, right? Did we talk about that? This, to me, a class like this is just about process. Can you follow processes? Can you learn a process, execute the process? And so if I'm teaching you a process and you're like, I can do it without the process, you're still kind of that type of person who's like, I'll figure it out. I can do it. I don't need any structure to it. And that can get you only so far. At some point, the human brain has a limitation as to how much it can handle at one time. So, all right, I think that was a great example. This is a perfect example of a test problem. I give you a nice vertex, but I force you to use a quadratic formula. Well, the reason why I don't like to put smaller numbers, the reason why I put bigger numbers here is just because I wanted your X-intercepts spaced out a little bit. If I had made all these numbers small, then you would have had X-intercepts like 0.025, and then it would have been harder to graph. So I tried to make it spread out a little bit to make it easier to graph. All right. Anything else on the graphing of a quadratic function before we get on to the applications? What formulas? Whatever, the quadratic formula. The negative b over 2a, all that kind of stuff. I don't have a problem with the quadratic formula. I tell you what, I'll let you have a cheat sheet on this test. Okay, one sheet of paper. Let's say front side only. I don't want to get all crazy here. Just front of the page, as much as you can fit on it. No worked out problems, though. You can write the 7-step process. You can write any formulas you want, but you just can't take examples that I've been doing and just copy them down. All right? That works. All right, so now let's do an application. So we talked about this last class, that when you throw a ball through the air, the path of the ball is represented by a parabola, right, by a quadratic function. So this is saying a ball is thrown in the air. The path of the ball is represented by the equation h equals negative t squared plus 8t. So h equals negative t squared. I'm just making it bigger so we can read it. What I want you to see here is that this is really a function. This may as well say f of t equals negative t squared plus 8t. The reason why they use h is because they're saying h is for height. So the height of the ball is given to you by this, and the reason they're using t instead of x is because t would represent time. So the height of the ball as a function of time. All right? Graph the equation over the interval 0, t is bigger than 0 and less than 8. So they want the graph of this quadratic function. That's what they want, right? They want you to graph it. And then from that, they want to know what the maximum height of the ball is. What's the maximum height of the ball going to be? In our graph, corresponding to our graph, what should it be? It should be connected to the vertex, shouldn't it? The highest point was the vertex. How long is the ball above 7 meters? Ooh, that's going to be a little bit harder. But let's get to it when we get to it. Graph it first. Okay, let's graph it. So what I'm going to do is I'm going to go through the 7-step process for this function and then put the graph. First step, is it a quadratic? Yes. Second step, it opens which way? Down. Because A is what? -1? A is the number in front of not x squared, but t squared in this case. So -1. Did I tell everyone that tomorrow's the last day to drop? Wait, today's the last day to drop. Just making it official. I think mostly everyone who's here is here to stay, so. But if you want to drop, you have to send me an email today in order for me to drop you. After that, I have to give you a grade A, B, C, D, or F. All right, opens down. Third step, vertex. So the H will be -b. What's b for us? 8, right? So -8 over 2 times a, which was -1. I'm getting 4. You getting 4? Okay. Now we need k. K is what we get when we plug 4 into the original function. So I'm going to call it f of 4, which is -4 squared plus 8 times 4. What's that? What I hear? Is that right? Now be careful here. I just make sure that you understand that the 4 is being squared, isn't it? The negative is not being squared. So it's going to be -16. That negative is like a -1 sitting out by itself. So this is going to become -16 plus 32, which is 16. Quick sketch. Your vertex is to the right 4, up 16, somewhere up there. This opens down. So we have X-intercepts, don't we? 2 of them. So this is very much like the last problem we just did. Let's find the X-intercepts. Because we have them. We have 2. So we set the original function equal to 0. The original function was in terms of t, though. So let me write it down in terms of t. -t squared. I've already forgotten. Plus 8t. Set that to 0. How are you going to solve this equation? Well, quadratic formula would work, right? But there's a faster way here. We can try and factor the left using GCF. So you only have 2 terms there, right? They both have a t. Why not just pull a t out? Or if you like, pull a t squared out. What do you, I mean, not t squared, a -t. What do you want? I don't care. Positive or negative t? You tell me. You go negative? What would that leave you with in there? T minus 8. And we're using the 0 factor property. If 2 things multiply to be 0, you set each one of these equal to 0 now. We've done all this, right? I mean, it's been a couple of days, but we have done this sort of factoring before. So set negative t equal to 0. I'm going to continue up here. And then the other one is setting t minus 8 equal to 0. I think the one on the right is pretty obvious. T is 8. Just move it to the other side. And then this one, t is 0. The only thing that can make 0 out of that is if t was 0 to start with. So you don't say negative 0, right? There are my X-intercepts. Questions? Y-intercept? You plug 0 into the function, which is, just gives you 0. It kills everything off. You just get 0. And so now I'm going to do a sketch. Let's see if we can fit this sketch on the grid they gave us. I don't even know where the center is. It looks kind of like this. We can do it like this. Now we have to be a little careful because our x-axis is actually our t-axis because we use t instead of x. And then the y-axis, we could call it h because remember the original problem said h. H was like our y, the height. Start with the vertex. Vertex. Where was our vertex? 416. Crap, is that going to fit? How many units up? 1, 2, 3, 4. I'm going to have to count by 2s to make this work. But on the t-axis, I'll just count by 1. So 1, 2, 3, 4. Here's 4. This is why I like drawing my own graphs, because if someone gives me a grid, I feel like I have to force things into it, where if I draw my own, I'm free to kind of be a little flexible with it. See the 4 here? I go up 16, counting by 2s. 2, 4, 6, 8, 10, 12, 14, 16. So I'm going to label that 16 up here. Come over. Believe my point's right there. 4, 16. X-intercepts or t-intercepts are 0 and 8, right? 0, there's 4, 5, 6, 7, 8. There's 8. Y-intercept was 0, so it's already there, right? It corresponds to that x-intercept. And then I have an axis of symmetry that I can use to help me draw. I don't know if I really need it. And my parabola does this sort of thing. Curving it a little bit to make it look like a U. There we go. Notice I stopped it, right? Why did I stop it? I didn't continue it down. I didn't continue it down. It says here to go between 0 and 8, right? X value of 0 to, t value of 0 to t value of 8. So if we actually drew the rest of this like this, we would be going outside the domain restriction. So by them telling us 0 less than or equal to t less than or equal to 8, they're cutting our domain and just saying, look at just that one piece. And it kind of makes sense in terms of the real problem, right? Yeah, the ball is going up and then coming back down. This is considered to be ground level, so we're not going to imagine that the ball is like going through the ground and into negative values, right? All right, let's see. What is the maximum height of the ball? 16, good. See, it's not the t value, it's not 4. 4 is how long it took to get there, right? At 4, whatever, seconds or something, it was 16 units high. So the height, this is k, isn't it? K will always give you the maximum. How long is the ball above 7 meters? This is a terrible question. How are you figuring that? Here's the problem I have. Meters is never even mentioned in this problem. Oh, there it is. Okay, good. Well, oh, in time seconds. All right, I didn't see that. Thank goodness, I was going to get upset. All right, meters. So how are you going to be able to determine this? You want to count up to 7 on our graph? 1, so 2, 4, 6, 7. Like, here's 7 on our graph. So like between here and here. So the time would be like from here to here, right? I don't like this question. And the reason why I don't like it is because that requires us solving what's called a quadratic inequality, which is something we haven't done. So let's just scrap it. But since I'm scrapping that, I will ask you one other question. When does the ball reach its max height? Mm-hmm. 4 seconds. Let's go back up there on 16 and let's put 16 meters because we did have a unit. 16 meters. So for this particular ball, it took 4 seconds for it to reach its maximum height of 16 meters, then it came back down. We good? I'm going to move to example 4. So let's do this. Falling objects on Earth. So it was determined a long time ago, long before any of us were around, that, where's my textbook? There it is. It was determined a long time ago that when you are on Earth and you drop things, right, things want to fall to the ground, gravity, right? So it's going to be loud, but drop these two things and so the book hits the ground first. I'm tearing this book apart. So why does the book hit the ground first? It's heavier? Doesn't have air resistance? Let's do a vote. I'm not going to call you out and be like, ha, ha, you were wrong. Some of you think that heavier objects fall faster than light objects. It's all right, come on. Heavier objects, we're here to learn, right? So if you're wrong and you learn something, you learn something. So, and then the other idea is air resistance. So you're saying if there was no air, they would fall together, same speed? That's right. So what is it that's making the book get to the ground faster? Is it the weight of the book or the mass of the book, or is the air the only factor, or is it both? What do y'all think? So I'm just having you think. Mm-hmm. Okay, so like if I take my pen, let's do your cell phone. You have a cell phone? No. You went reaching for it. Look at you. Right. If I drop my pen in this book, I'm not going to drop my pen because I need that. Let's drop this. If I drop the marker in the book, which will hit first? They'll be same. So that was a question for a long time. Does the mass or weight of something have an impact or dictate which one falls faster, right? I don't know if you've ever seen people say this before. You know, hey man, you know, that thing's falling real fast because it's really heavy. Does it matter how heavy something is? Is it going to affect the rate of change? So here's a simple way of determining it. So if you think that this is going to fall to the ground faster than this because it's heavier, then if I put the paper on top of the book and drop them, then what should happen is the book should start to fall away from the paper because it's going to go faster than the paper, isn't it? If that's what you think is going to happen. Okay, so they go together. And the reason why they go together is because now the air is not a factor for the paper, right? The book is moving the air out of the way. The air doesn't impact this at all. And so when they drop together. So on all objects on Earth would fall together all the time if there wasn't air, all right? But you throw air into it, of course, that creates a different dynamic situation. And so the paper is affected more by the air because it's, you know, the way. So that's how a parachute works, right? You jump out of an airplane, you're like this, you're going to start hauling ass, right? But you reach this thing called, anyone know what it's called? Terminal velocity. That's basically where your body is acting like a parachute, but you're really moving fast still. But there's a certain speed that you don't get any faster because the air resistance, even on the bottom of your feet, is enough to stop you from accelerating. You just stick at this speed. I think terminal velocity is like 130 miles an hour or something like that. So if you jump out of an airplane, like the fastest you can go is like 130 miles an hour. Okay? Well, so when you open your parachute, now you create a huge resistance to the air, and it slows you down. But even that reaches a terminal velocity, and it's a safe velocity that you can land with. So this was discovered a long time ago, and proven with using vacuum tubes, where they would take this big glass tube, they would take all the air out of it, they would drop a feather in a rock, they would fall together. So it was known for a long time, but it was kind of like, you know, there's been this fight between scientists and like theologians for a long time. You know, like the Earth is the center of the universe. And then the scientists said no, and then they executed the scientists because they don't like people saying that, you know, whatever. Right, so there's been this battle. So I don't know if you've ever seen the video or pictures of the guy on the moon when they first got there, and he drops a feather and a hammer together. You can YouTube it. And the feather and the hammer hit the ground at the same time. That's because on the moon there's no atmosphere, there's no air, so there's no resistance. And even though it had been proven, it was kind of like the, you know, to everyone else, like, we've been telling you, now we're just proving it again to you that the air is what made it. Yeah, so, okay. That's right. Well, you know when the capsules come in from, like, they're retrieving something from space, you'll notice the parachute opens up. There's an initial parachute. That just slows it down a little bit, and then the next canopy's open. Then by the end of it, there's like 3 or 4 of them. That slows it down enough. No. Yeah, no, the first one is just to slow it down, because if they open all 4 at one time, it would rip the cord. It would kill the people in it because it would be too fast of a deceleration. Yeah. Yeah, it'd be like hitting a brick wall because, you know, in space, the shuttle's traveling, I believe, like, I'd be guessing because it's been a while, but I would say the space shuttle out in space is going at least 16,000 miles per hour. Yeah, that's fast. I mean, that's fast to us, right? We know what 100 miles an hour feels like in a car. 16,000 miles per hour. So when they come back into the atmosphere, right, imagine going from 16,000 miles an hour to even, let's say, 100 miles an hour in 2 seconds would be like hitting a wall at 15,000 miles per hour. It's over, right? So, so look, because all objects on Earth fall at the same rate, if we take air out, we actually have a function that would represent that scenario, and here's what it is. I'm going to use h of t instead of that. So I'm putting no error here. And I've always heard students, especially like engineering students, and they'll be like, I don't know why it is that we're studying these stupid quadratic functions, and they're like, there's no error. Like, come on, man, we live with error. Like, why don't, let's talk about the error. Well, you want to talk about the error, the function's going to get much more complicated. You have to account for that error. You crawl before you walk, right? And this is the type of thing. In a college algebra class, we're crawling before we walk. You get into physics class, you start with no error, then you throw error in. If you've ever taken physics, you'll start with some, they call them free body diagrams. You start with no friction, and then you add friction in later, right? And so you have to kind of progress into it. So trust me, we do deal with the error, just not here, all right? All right, let me explain what all these things are. V of t. V and h. And those are the main things we need to focus our attention on right now. H is the starting height. How do you spell height? It's not the I before E except after C. That's why I don't like the English language. V is your starting speed. Now, there's something important about speed. If up, V is positive. If down, V is negative. So let me try and illustrate what's happening here. We have an object on Earth, and we're giving it a starting height. Okay, height equals 0 would be whatever we consider to be the ground. Like right now, I consider this to be 0. I realize I'm on the third story of a building, so we could say 0's out there. But if we say this is 0 right here, then I raise this up, then the height is the distance from here to here. Okay. Then I have this starting speed. If I just let this go, the starting speed is 0. I just let it go. But if I throw it down, okay, I gave it an initial starting speed downward. That speed, whatever it is, I would put in that formula as a negative number because I threw it down. If I throw this thing up with the starting speed, like from the same height, throw it up, now you're going to put a number in there that's positive. And of course, there's a difference, right? I throw one up and I throw one down, they're not going to get to the ground at the same time, right? So that number right there, that V, accounts for that differentiation there. Your height is always measured in feet. Your starting speed is measured in feet per second. We can also write that feet over seconds. So most of the time in a problem, someone has to tell you this information. You have to know this information in order for you to figure anything else out. Now, t in the problem, or t in the equation, is time. And it's always measured in seconds. And the last part of the equation is the left side, which is h of t. And this is the height of the object after, or I should say at, t seconds. So again, here's the thing. I realize error matters. But if you're going to drop my set of keys in this marker, the error really didn't matter. Those things pretty much do the same thing. They behave well. Now, if it's a parachute or if it's, an airplane, then of course you're going to want to take the error into account. But for practical purposes, experiments that you do that are on smaller scale, we don't really have to consider the error. So this equation a lot of times is good enough for what we need. All right. Let's just double check the formula real quick. Oh, great, that's not what I want to do. VH. So when I'm about to drop an object on Earth, right? My time, set my timer. Right now my time is at what? I'm about to drop it. I haven't dropped it yet though. Time is what? 0. Okay, plug 0 into this function. Replace t with 0. Kills this off, doesn't it? Kills this off and leaves this. And what was h? My starting height. So when t is 0, I'm at h, aren't I? And then I let go, and then the clock starts. After 1 second, where would I be? Well, 1 squared minus 16, right? Then I plug 1 in right here, plus v, and then plus h. So again, I'd have to know if there was a starting speed or not. But this negative 16t squared, guess what that accounts for? Anyone know what that part is accounting for? It's acceleration. It's the acceleration of gravity. Have you ever heard the acceleration of gravity is 9.8 meters per second squared? Anyone that's taken class? 9.8 meters per second squared. No, sorry, I already said squared. 9.8 meters per second squared. If you convert 9.8 meters per second squared into feet per second squared, then you get negative 16. So that's the gravity. So this formula is actually very, very powerful because if we happen to be on a different planet, which I understand we wouldn't be, but like if we're trying to figure out the way that a space probe is going to be affected by the gravity of some other planet, then the acceleration of gravity, all we have to do is change this number and it applies to any other planet. Make sense? All right. There we go. We got the formula. Now it's time for a problem. I always like to do this problem because it usually gets people to pay attention. What? Oh, yeah. Yeah, I like to give these problems just because I want to make people go drop the class. All right, so this is going to be sort of a somber topic, and I'm not going to record. All right, I think that that's probably enough time. You can finish that up on your own. You have the answers up here. There's really nothing different with this than what you did for last class in the homework. You have a quadratic function. You're finding the h, the k, and then the x-intercepts. I mean, it's all the same as far as the mechanics of it. The only difference is interpreting the word problem, making sure you understand, what it is they're asking for and how it connects. Just keep in mind, most of the problems you're going to need to find h, k, and the x-intercepts. So, all right, I think I'm ready to move on to some new stuff. I know. We are now going to look at a new category of functions. The notes do a pretty decent job of explaining what polynomial functions are, but I'm going to kind of treat this the same way I did with the quadratics. I'm just going to approach it kind of from my perspective. I want to start first by explaining what a polynomial function is. It's a function with terms consisting of integer powers of x. And I need to add one more thing to this. Non-negative integers. So some examples will bring this to light, I hope. Here's an example of a polynomial function. So I have a function. I have terms, right? I have exactly one, in this case two, three terms, right? And notice that each of the terms has a x in it to a power, and that power is an integer, right? 3 is an integer, 4 is an integer, 5 is an integer. But the restriction is that this integer must never be negative, right? As long as it's not negative, and you put these things together, that is what we call a polynomial function. Now, what about the 7? It doesn't have an x? It doesn't, but if we wanted to, if we squinted our eyes, do you agree that it really does have an x? It's like x to the 0. X to the 0 is 1. So sitting next to that is a power of x, but we don't write that. So just don't be afraid to see a number by itself. That still falls into the category of being a polynomial function. So numbers by themselves are okay. Any function we can write. I could have 3 terms, I could have 5 terms, I could have 100 terms, I could have 1,000 terms. As long as each one is a number in front of power of x, it's a polynomial function. Another example. Is that a polynomial function? Yes. You have terms. Each term has an x to a power, x to a power. Those powers are integers, but they're not negative. The 5 by itself, that's really like a 5, and then there's an x to the 0 next to it. So that is a polynomial. But it's also, we would also call that one a what? A quadratic, right? A quadratic function. So what I'm saying to you is that a quadratic function is a polynomial function. What about this? Two terms? It is a line, yes. But is it a polynomial? That's right. But does it satisfy what I said here? It's terms consisting of integer powers of x, non-negative integers. That has x to the first power. That's not a negative number on it. It's an integer. This number 1 really has an x to the 0 next to it. So this also falls into the category of being a polynomial function. Now, when we studied them, we called them linear functions. But in fact, it is also a polynomial function. Another one. That is not a polynomial. No, I'm kidding. It is. Now, this is a polynomial function also. This is also a line, though, but it's a flat line, horizontal line, going through 10. This is a line, and it is also a polynomial function. So if we're looking at this kind of in a picture, if you take all of the polynomial functions that live out there, you like this. When I talked about numbers, you really like this, so you're going to love this also. If this is the blob of the bucket of all polynomials, that bucket inside of it has smaller classes of functions that we've looked at. Lines, right? And quadratics. All quadratic functions are polynomial functions. All lines are polynomial functions. But then there's other ones too. You know, we have x cubed. That's no longer a quadratic. It's no longer a line, but it's a polynomial. When you have x cubed in there, we call them cubic functions. If you have a 4, it's quartic, and then you start losing words for the numbers, right? What if you have like x to the 171st power? You don't really have a name for it anymore, but it would be a polynomial function. So this is a very, very broad class of functions here. We've studied these. We can graph a line. We know what it takes. We can graph a quadratic 7-step process. We know what that takes. Our goal now is, what if someone just gives us an arbitrary polynomial? Can we graph it? And it turns out to be a lot harder to do. Well, I wouldn't say harder. It's just we've got to make sure we pick these pretty nice, or else we're going to have major trouble with them. Now, when we're looking at polynomials, no matter which one we're ever given, oh yeah, what's polynomial? You know, poly means what? Many, or right? Many, and then nomial is like monomial. Remember, you learned monomial, binomial, trinomial. Okay, nomial is like a term. So this just means many terms. This is a many-term function. That's all this is saying. The important thing is that the power on the x's have to be integer powers. Would this be a polynomial? Square root really means x to what power? Do you all remember? It's a fractional power, 1/2. This would be in properties of exponents back in, I don't know, a different class than this, I guess. The requirement was that you had to have integer powers. Integers are like the counting numbers, 1, 2, 3, 4, 5, 6. 1/2 is not an integer, and therefore this would not be a polynomial function. So the way we go about graphing something, we could not graph this, all right? Not in this class. All these others we could. So when it comes to polynomials, we're going to have some terminology that we all need to get comfortable with. And if we understand terminology, it'll make things a little easier when it comes to graphing these, which is our ultimate goal. Our goal to sketch a polynomial. Function. But to get there, here's some terminology. First, we have something called the degree. The degree of the polynomial. And the degree of the polynomial is simply the highest power of x you see. You look at all the exponents in the entire polynomial, the biggest number you see is the degree. So if you see x to the 4th, and that's the biggest one you've got, 4 is your degree. And we call it a 4th degree polynomial. Okay, that's what we would call it. And then on top of that, you have this other thing, which we call the leading coefficient. The leading coefficient is just the number in front of the x with the highest power. So let's just do a quick practice here. I want us to find the degree and the LC, leading coefficient. All right, that's what I'm going to call it from now on, so we don't have to write leading coefficient over and over and over. This LC. Here we go. F of x equals negative 4x to the 4th minus 3x to the 5th plus 1. What is the degree of this polynomial? Degree, I'm just going to say D, is what? 5. What's the leading coefficient? -3. So we have to be careful here. That's why I gave you this first example. The highest power of x I see is 5. The leading coefficient is the number that's in front of that x that contains the highest power of 5. You don't want to confuse this and think leading means you just look in the front, because you can always rearrange a polynomial. So what's in front doesn't always have to be there. You could switch it. So leading is always the number in front of the highest power. So you should only have one leading coefficient and one degree. There shouldn't be more than one of each. Understand? Okay. Now, we could do a bunch of those. You probably just want me to give you a test full of those, right? Okay. All right, so with that in mind, what do poly functions look like? When we graph them? Well, we already know that a line is a polynomial function, right? We know that a parabola is a polynomial function. So we have some idea of what they look like, but a line is very different than a parabola, right? So I can't say, oh, they look like lines, and I can't say they look like parabolas, because those are different. So there's got to be some other characteristics of polynomials that are universal to all of them. And here's one way I can say it. First of all, they are smooth. Smooth. That means there's no breaks, jumps, or gaps. Okay, so when you draw it, it's not going to just all of a sudden pick your pencil up and just appear somewhere else. You basically have to draw these without picking up your pencil. There are functions that exist out there where they do have breaks in them. It's the next category of function called rational functions, but they won't be on your test, so you don't need to worry about them right now. Okay, so they're smooth, they're connected, right? Pick it up, draw it without picking up your pencil. Okay, they're all smooth, and then if the degree is 2 or higher, the graph is curved. So degree 2 polynomial would be a quadratic, wouldn't it? We know that when we draw a quadratic, it's curved, right? It's got a curve to it. What I'm saying is if we have a degree 3, it's also curved. It's got curves in it. And then 4, it's got curves. 5, it's got curves. The only one it doesn't have curves for is 1, degree 1, and that's a line. And we know the line is straight, doesn't have a curve, right? But anything above 2, and it's curved. All right, for the next part, I'm going to show you something that will help you see what they look like. This is some stuff I threw together a few years ago. Let me see if I can open this up. Where's open? There it is. Polynomials, here we go. All right. I hope you can see this. Here's the polynomial function right here. X to the 4th plus 4x cubed minus 37x squared minus 64x plus 336. That is a polynomial. Everyone agree? What is the degree of this polynomial? 4. What's the leading coefficient? 1, right? Okay, good. Now, notice that its graph, right, is curved. And that's because it's degree 4. It's bigger than 2. It's got to be curved. Also, it's smooth. You can draw it without picking up your pencil. Now, let's just see what happens. Notice, I don't have it here, but imagine this right here has little arrows on it, and this has little arrows on it, kind of like a parabola. It's going up on both sides forever. What if I change? I'm going to change something here. You're probably not going to realize what I'm doing, and that's okay. Don't worry. So look what happened. I changed this. Look at the degree now. Still 4, right? But I put leading coefficient now as what? -1. So what happened? Instead of it going up and up, it's now going, on the ends, it's going down and down, right? You see that? Let me change that number again. Instead of making it -1, what about -2? Kind of hard to see it here, but there it is. I'm trying to learn how to use this phone. Shut it up. Still going down, down, right, on the sides. All I did was change it. The leading coefficient is -2 instead of -1. What if I make it -3? See what happens. Still going down, down? Yes? I'm zooming out, by the way. I don't know if you've noticed the y-axis is getting huge. Now let me make it, instead of -3, make it +3. What happened now? They both went up. That's behaving a lot like a parabola, isn't it? Remember that with a parabola, x squared, we knew it looked like the parabola was either up or down, right? The only thing that dictated that was what? The a in front, right? If it was positive, it was up. It was negative, it was down. Same sort of thing is happening here with this 4th degree polynomial. Both sides are going up, or both sides are going down, and that looks like it's being dictated by that number in front. I wonder if this would happen for a 6th degree polynomial, because 6 is an even number, right? 2 squared, both went up, both went down. 4th degree, both up, both down. Let's try a 6th degree. I'll get to 3 in a second. Come on. There we go. There's a 6th degree polynomial. You see it? Notice both sides are going up. Yes? There's a leading coefficient that's +3. I'm gonna guess that if I change this to -3, it's going to flip over, and it does. And so again, what's happening is that the leading coefficient and the degree tell us a lot about what happens on the outside of the graph. What it does not tell us is all this squiggly shit that's going on in here, okay? Like, I don't really know how to figure that out yet. We are going to address that. But the leading coefficient and degree is enough for us to determine what we call the end behavior, the left and right end behavior. Now let's change it to odd. How about we go with, well, 1st degree is a line, isn't it? Oh, I need to scale back out. There we go. That's an odd, right? Look at the degree here. Is 1. What's the leading coefficient? 5. It's positive. So what happens with the line is that what's the left side doing? The left side. Left side's going down, right side's going up, isn't it? What if I change the leading coefficient from positive to negative? It's going to go the opposite way. The left side goes up, right side goes down. So with an odd power, doesn't it look like the sides do opposite of each other? Now let me change it to a 3rd degree polynomial, because that's the next, right? And let me change this back to a positive. Let me zoom out. So with the 3rd degree polynomial and a leading coefficient that's positive, it does the same thing the line did. Down on the left, up on the right. The squiggly stuff in the middle, don't really know yet, right? If I change it to a negative in front, it flips. Up on the left, down on the right. And this theoretically should happen for any odd number, so let me change it to a 5th degree. Ooh. There we go. Change that to 2 again. Look, left side down, right side up. So that right there just visually shows you that you can determine a lot about the graph by just knowing the leading coefficient and degree. And that leads us to what's called the leading coefficient test. Here's what it says. And I'm going to do it with a table. All right? The table is always seems to me to be the cleanest, easiest way to do it. So just try and copy down something that looks like this. Up here, I'm going to put degree. Is there? Is it good? Oh, man. I did? What page is it? Oh, no. This one, they're just asking you to identify what's the degree, leading coefficient, right? What I'm giving you is going to be a little bit different than that. So degree, if the degree is even, then over here the degree is odd. Over here, if the LC, what's LC? If it's positive, and then the leading coefficient is negative. So this is a table, and this is something we can refer to for a quick reference. So what did we say? If the degree was even, that's like a quadratic, right? And the leading coefficient is positive, what did the left side do? Up. The right side? Up. But in general, for any polynomial function, all we know is the left side goes up, the right side goes up, and in the middle, I do not know, so I'm putting a question mark. It may be like a parabola where it just comes down and kind of flat, not like bottoms out. Or if it's fourth degree, it may wiggle a couple of times, but eventually it's got to come up again. So the question mark will be the next thing we address, but we have to get the left and right hand stuff down first. Now what about, let's go down. What if I'm still an even degree polynomial, but I've got a negative leading coefficient? Down, down, right? Down, down. In the middle, I don't know. Then when we do odd, think about a line. Initially, if it's the leading coefficient is positive, that means it has a positive slope. So left side goes down, right side goes up. In the middle, I have no idea. And then when you come and put a negative leading coefficient, it flips over like this. Is there? Yeah, it's there. They may have done it a little. Yeah. So this stuff right here, all right, these things, all these are called the end behavior, all right? Those are called end behavior. End behavior. So with a polynomial function, there are only four possibilities. Both sides go up, both sides go down, left side goes down, right side goes up, or left side goes up, right side goes down. That's it. That's all that can ever happen. All right, we good? But what about the middle? What about the middle? You wish. What does this thing, look at this fifth degree polynomial. What is this point right here? We call it a what? An X-intercept. What is this? And this, and this, and this. The degree tells you the most number of times you can cross. Okay, so if you have a fifth degree polynomial like this one, you can only cross 5 times. That's the most you can ever have. You can never have a fifth degree polynomial and cross the x-axis 6 times. It's impossible. But it doesn't guarantee you that you're going to have 5 answers here. It is possible to have none, in fact. But again, not for, yes? How many turns you'll have? Yeah, we call these turns. Take one away. So if you have a fifth degree number of terms, the most number of turns you have is 1, 2, 3, 4. You couldn't have 5 turns though. Yep. If you have 5 turns. But see, you don't have to have, let me show you, watch. I'm gonna make this -3, -3, -3. Let me zoom in on this. Kind of hard to see it, but I think that's good enough. So this is a fifth degree polynomial, right? Fifth degree. Left side goes down, right side goes up. How many times does it cross the x-axis? This is actually 1, 2, and 3. It only crosses 3 times. How many turns does it have? This would be considered to be a turn, and then down here is another turn. It only has 2 turns. This wouldn't be a turn. That goes like this. It goes up, flattens out, and goes back. So it never turns back on itself. Hard to see it. That's why I was like, that's going to be hard to see. If I zoom in a little bit more, you can see it. Right? It just goes up and just kind of barely goes through. See, now, I mean, in a calculus class is where you really start to get into, like, how do you figure all these little details out? All we want is a general sketch. All right? But going back to what I was saying, it has x-intercepts, doesn't it? And because it has x-intercepts, we know how to find x-intercepts. All you do is set the function equal to 0, right? That's it. That's it. Simple. Not going to be so easy. I'm going to give you another scenario here. Keep that as -3, -3. Make that 1. What's that? I actually wrote the code for this. It's not as bad. Well, I know there's no computer science majors in here because you wouldn't be in here, right? So that's the code right there that makes that happen. Anyone ever heard of a website called Wolfram Alpha? No, I know. Wolfram Alpha is like the website for math, and it's amazingly powerful. And that website, the brains behind it, the computer behind it, is actually this program that I'm using, which is called Mathematica, Wolfram Mathematica. I've been using this since version 3.2 when I was a student. Now we're in version 10, so I've got a lot of experience with this thing. Oh, I didn't mean to do that. Okay, I wanted you to see this. 4th degree polynomial, right? 4th degree polynomial. Take a look at its x-intercepts. I have 1, 2, 3, right? Notice on this x-intercept, if we were to try and like talk through this, I could explain that what's happening is I'm coming down, right? And I'm kind of like just touching the x-axis there, right? Or you could also say it's almost like a ball bouncing off the x-axis. Touching or bouncing, whichever makes more sense to you. But on this x-intercept, I actually cross through the x-axis, don't I? And then back going this way, I actually cross through the x-axis. With all polynomial functions, when you get to an x-intercept, you're either going to bounce off of it or you're going to cross through it. It's one or the other. And there's a way to determine which one it is. And it all has to do with this down here. Here's the original polynomial function, right? Believe it or not, that can be factored. We can factor this. It's a pain in the ass to factor, but it could be factored. And it would factor to be these 3 factors, this, this, and this. Notice, what would make this 0? If I plug in 7, and notice here at 7, I have an x-intercept and I cross. How about x minus 1? What would make this 0? 1. And what happens here at 1? Cross. X plus 3, what would make that 0? -3, but notice it's squared. And what happens at -3? I bounce. And so somehow, if you can take a polynomial function and you can factor it, then the power on the factors determines whether or not you cross or bounce. But it's the getting from here to here which is difficult. I'll make it bounce twice. Watch. So look at it. I changed it, and now they both have squares on each factor, right? And you see how it changed there? Zooming out. There we go. So look, at what? 1 would make this 0. At 1, I bounce off. And at -3, I bounce off. Understand? Okay. Where do we want to go with this? We've got 20 minutes. I can't quite go where I want to go, but I will go with this, all right? So to sketch a polynomial function, here's what we do. One, remember steps, right? Steps. We have first, is it a polynomial? Right, you're going to look at it. Is it a polynomial function? Yes or no? All right, once you know it's a poly, next thing, determine left and right behavior. How do we determine the left and right behavior? Yeah, this thing right here, right? So we are going to actually do that leading coefficient test to determine the left and right behavior. After you've done that, the next step is to find the X-intercepts. And that right there is the hardest problem. How do we find X-intercepts? Always set the function to 0. And that's going to require factoring. And we know how to factor everything we've done up to this point. We can factor 2 terms, 3 terms, 4 terms, right? 2 terms, 3 terms, 4 terms. We do 4 terms with grouping, and we hope for the best. 3 terms we do with the AC method. 2 terms, difference of squares, things like that. GCF is always there. Right, so we'll find the X-intercepts. We will set it equal to 0 and factor. Now, here we need to make a note. If a factor is raised to an odd power, we cross at that X-intercept. If a factor is raised to an even power, we're going to bounce. Are y'all okay with bounce? Okay. At that X-intercept. There we go. So what we'll do is we'll factor it and we'll figure out what's going on and we'll get all this information together. The fourth step will be to sketch it. And when we sketch it, what we do is plot the X-intercepts then show end behavior, and last thing, fill in gaps. I'm trying to get one example to you here, okay? One example. If I can get one example, at least I'll feel a little bit better about things. All right, let's do it. Did everyone get that? Anyone need that? Okay, I'm going to make one up using Mathematica here, or using my program. Let's do a let's do a third degree polynomial. We'll shoot for the moon here. Okay, fourth degree polynomial. Let's make 0 a root and -3, -3, and 2. There we go. Our picture at the end should look like this, okay? But here's the function we're going to graph. X to the 4th plus 4x cubed minus 3x squared minus 18x. Everyone got it? Okay. F of x, 4x cubed, that one? I don't know. Just someone tell me what is 4x cubed? Mm-hmm. Wait, hold on. I'm missing something. Oh, x to the 4th in front. All right. Is that okay? All right. Steps. First step. Yes, it is a polynomial. Also, the instructions here are to sketch this, all right? Second step. It's going to go up and up. So the degree here is 4, right? The leading coefficient is what? 1. So we have an even degree. We have a positive leading coefficient. So if you go off that table, it's up, up. I don't need you to write down degree and leading. If you just put up, up, I'm happy. But it's just, if you're referring back to this, you'll know where I got it from. Up, in the middle, I don't know, up. So keeping that in mind, I move on to the third step, and the hardest step. Find the X-intercepts. So I take this big ugly thing, I set it to 0, and now I break out my factoring tools. Yes, that's our GCF, so that's always the first thing we want to look for. Good. Okay. Now, how many terms are in there? That's right. We have 4 terms inside here, right? And because we have 4 terms, I will attempt to do grouping. So grouping was where we split the first 2 off from the second 2, and then we tried to find a GCF in just these 2, remember? Okay, so let's do that. And just remember, you have an X on the outside of everything. So if you need to, just kind of over-exaggerate what's going on. Don't forget, this is all equal to 0, right? Bring that with you. What is a GCF I can pull out of these first 2? X to the 2nd power, right? What would be left in there? X plus 4, okay? Hold on a second. Yeah. Something does not look right. Fourth degree, hold on, 0, 0, 0, 2. What the hell? Do y'all see what I'm... Yeah, my code or something is messed up. No. Well, fourth degree, 0, 3, x plus 3 squared. Why? This is confusing. All right, hold on. No, I'm confused as to why it's not x minus x. Just hang tight. X plus 3 squared times x. Okay. What would we factor out? X plus 6. And that doesn't work, right? There's nothing wrong with what I wrote. Everything's okay with that. The problem here is that grouping fails, right? Grouping failed because these don't match. But if you look at this, according to my code, and it's been confirmed, that this right here does factor. It does factor. It actually breaks down to be this. The problem is we can't get it there because the only methods we have fail us, right? Grouping, which is the only thing we know how to work with, doesn't work. So the question becomes, how do we get that from here to here if everything we've learned up to this point doesn't allow us to do it? And that's what we'll have to do after this test. Because there's a way to do it. And that's kind of where we want to, we want to introduce a new technique of factoring, a new way of factoring things. It's pretty efficient, but there's not enough time, obviously, now to do it. So what would I ask on the polynomial thing on the test? Identify degree, leading coefficient, and behavior. All right? Those are your favorites. All right. We will not yet be able to graph one of these, so don't expect it on the test. So when you go through, look at the homework out of that section, and don't worry so much about anything that does not refer to leading coefficient test or end behavior. I'm going to do two things. I'm going to email you the problems, and there was something else. That's why I was about to make